Welcome to the session about functional programming with Java. It's actually Java 22 that we have right now, so let me just update the title here. My name is Jacek Kunicki. I'm a software engineer at Software Mill. I started my journey as a Java developer. Then at some point I switched to Scala and to functional programming. And it didn't make sense at all when I started. But after some time, I think it clicked. I started teaching people functional programming. And while I did it in Scala, I was wondering whether it's possible to move or transfer some of the good practices that were like daily bread for us in Scala to Java. Java as the language has evolved significantly over that time. And with some of the constructs that we have in Java right now, it turns out it's quite easy and quite eye-pleasing to implement some of the concepts. And that's what I would like to show you today. I need to start with a short disclaimer that the things that I'm going to show here would probably be counterintuitive at first or even after a longer time, but that's okay. I mean, you need to get used to it, you need to process it in your brains, and then there is a chance that at some point they would actually become intuitive. So let's start with answering the question what functional programming actually is. And there is a definition that says that functional programming consists of two things. First thing are pure functions, and the other are immutable values. So starting with the pure functions, I would like to start with introducing a couple of concepts, actually two of them. The first one is idempotency. And idempotency is a property of the code or the logic that you are executing that says that if you execute your code, like your method or function multiple times, the state after the consecutive executions would be the same. And this might also include side effects. So if this doesn't mean that the function is not allowed to perform any side effects, it is, but the state must be the same. And a good example of that is an HTTP post, where when you make a first call to a HTTP post, it probably would create some resource on your server. When you call it for the second time, the state of the world should be the same. So the resource would still be there, but it wouldn't be created multiple times. It would only be created once. So then you can say that the call to HTTP post is idempotent, which means no matter how many times you call it, the result, also including the side effects and the state of the world, would be the same. The second property is called referential transparency, or RT for short. And this is a property that says that if your function satisfies it, it means that you can replace the calls to your function with the value that the function would return for given arguments. In other words, this means that for the same arguments, the function is always going to return the same value, and that there would be no side effects. A good example of that is if you imagine a function that gives you a capital city of a given country in a given point of time. And then, for example, if you call this function with the country will be Poland, the time would be 2024, the result would always be Warsaw. So wherever in your code you call the function, you can actually replace the function call with just the value Warsaw. And this means that this function is referentially transparent. So those are the two properties, and actually referential transparency is a stronger one. So you can say that all the referentially transparent functions would be idempotent, but the other way around, it doesn't always work because of side effects. And as I said, if you imagine, for example, an HTTP post, it can have a side effect at the first time. For the subsequent calls, it wouldn't. So referential transparency is a stronger property of those two. And now if we think what makes a function pure in terms of functional programming, well, we want to have two properties. The first one is that the output of the function only depends on the inputs. And the other one, that there are no side effects, or actually unmanaged side effects. We'll cover this unmanaged thing shortly. So if you look at this definition, this actually is very similar to referential transparency. And that's no coincidence, because you can use these terms interchangeably. So you can say that the function is pure when it is referentially transparent in this meaning. So this was the definition. Let's see an example. So we have a function here that does a couple of things, and this function is actually not referentially transparent, and we'll see why. So if you look at what this function does, it receives some parameters, it calls a setter on one of the parameters, it outputs something to the standard output, and it also returns a result based on some condition. So the first issue with the function, and starting with the last statement, is that it has a dependency on something external. In this case, the external thing is the system clock, which is something like hardware related. So this isn't really referential transparent, because this breaks depending on something external, breaks the referential transparency, because the result of the function doesn't only depend on the values of the parameters. It depends on something that we have no control over. The second thing is a side effect, and in this case, a side effect is using the system output. So this is something external that we are using. This is some I/O that we are interacting with. You can think of another examples of I/Os. For example, this could be a database access, this could be an HTTP call, or any other RPC call to any other service. But the thing that it interacts with something external is a side effect. And now if you think about side effects, and going back to the definition where we spoke about unmanaged side effects, the thing is that you cannot really avoid side effects, because like you do stuff like that, and usually this is a important part of your program. This interacting with the database, interacting with an external service, you need to do it. The thing is that a function can still be pure if the side effects are somehow managed. So if you have a way of wrapping the side effects in some construct that would give you some more control on how you execute it. Unfortunately, this is not yet possible in Java, so this is the thing that Java is missing. But in some Scala libraries, you have some constructs that let you wrap your side effects and have better control over them. And in this case, it means that you can use side effects, but you need to denote this explicitly, that you are doing that. And you need to have some control on when these effects are executed. So we had a dependency of something external. We had a side effect, meaning interaction with I/O. And the last thing is mutating some shared state. So here you can see that we are using a setter on the data type, and we are setting a value. And this means that we are mutating something that is external to our function. So again, this is not a good thing, because we are modifying data that is passed. So the function is not pure, because it modifies the outside world, the result, and it has a side effect, and the result doesn't only depend on what got inside. And if you're thinking about immutability in this case, you can, if you look at the data parameter, well, this is final, but you probably know that this is only a reference, that the reference is final. The data itself might be mutable. So actually a parameter passed in this way, when the data class itself is mutable, it doesn't really represent a single value of the data class, a single instance. It's a value that can change over time, because in multiple calls, the value can be different, and you can modify it. So the caller never knows what is going to happen. So let's see what we can do about that, because we identified the problems, why the function isn't pure, because it has side effects and some other properties. And the question is, what can we do about the data? So if we look at how the data is implemented, this is like a classical example of a Java bean. So you have the private fields, you have a constructor, you have getters and setters, you have equals hashcode to string. How can we make it immutable? Well, we could start by doing this ourselves. So we could try to implement this ourselves. So we can take a class and say that it has a private field ID, it has a private field value. We'd like the fields to be final, because we want our class to be immutable. In this case, we need to initialize them somehow. So we need a constructor. And then we need to access the values somehow. So what you would typically do is generate a getter for your fields. But the question is whether this is really necessary. Well, I would say no, because since your fields are already immutable, so you cannot change them, is there anything wrong with just changing them to public, so doing something like that? I guess that is okay. The thing with this approach is that it comes with a cost. So whenever you want to modify some data inside your class, you actually need to create a new instance. So you might end up with having multiple instances of your class, because you are no longer allowed to call a setter and change the value that is here. you need to create a copy of that. So this is a cost, but there are other benefits that the immutability gives you. And of course, here you need to implement some other stuff like the equals hash code, because this is not given out of the box. But with the actually records are not a recent introduction to Java. They have already been there for quite some time now. But this is a way to solve it. So we don't have to implement this ourselves anymore. We can instead use a class like data record that just has the fields, and that's it. And this gives us all the properties that we want for free. So we have an immutable data structure. We have ways to access this. If we wanted to have a copy, well, we would still need to make it somehow. And what it also gives us is a nice toString method, and plus the equals and hash code. So I just have a tiny test here that shows how the toString things works. You can see that for immutable data, this is like a classic toString that gives you the name of the class and the hash code. And for a record, what you get for free is a nice toString representation, which is very useful. So that's our starting point for functional programming. So we had immutable values that give us a couple of nice properties. For example, they can be safely passed around, which means if you have an immutable data class, you can pass it anywhere without risking that someone is going to mutate it without you knowing about that. So that's quite a nice thing. Now, what about pure functions? So pure functions also have a couple of nice properties. The first one is since they return the same result for the same arguments, they can be optimized somehow. So the values can be memoized or cached, whatever you call it. So and then you can reuse the already computed value, because you know that for given parameters, the result would always be the same. Another great property of pure functions is that they are thread safe. So you can safely parallelize them, because you know, since they are pure, since they always return the same value for a given set of arguments, because they have no side effects, it means that you can, and then don't mutate any shared state. It means that you can just parallelize them, run them in parallel without thinking much about this, and without thinking about what can go wrong. And the third property of pure functions is that they are a great candidate for testing. And this can be both simple unit testing, but you can also use them very nicely with an approach called property-based testing, which the idea of this approach is that you have a tool that generates the test data for you, and you have like many cases covered out of the box, and the test framework like tries to see if your function is failing for some input. But you have not only a single case covered, but you have multiple cases of multiple different values of the arguments covered automatically by the tool. And the last property of and a general one of the functional code like this, one that is constructed with pure functions and immutable values, is that it's easier to reason about. And this is a buzzword, so if you read any blog post about functional programming, you might have heard about this. But there is a lot of truth in this buzzword. So if you think about it, well, sometimes it gets too complicated and it's not really easy to reason about. But if you think about the properties that we covered here, like, for example, thread safety, the fact that you don't think to worry about whether someone is going to mutate your data, this is really nice, and this makes your code more understandable at first sight than if you had some shared mutable state, if you had mutable data. So that's for an introduction to the concepts of functional programming. So why at all is it good to think in terms of pure functions, immutable values, and what benefits it gives? And I want to show some of the approaches on two examples. The first one would be about error handling in a functional way. So let's get back to our service. And in our service, we have some example function that finds a user by ID. It returns the user, and that's it. And this function is used somewhere else in our API layer. So the API layer, this is like something like an HTTP API. You can think of it like that. It gets the user from the service, and then it wraps it into some kind of a response and returns it. Now, if you look at this code, there is a couple of questions you might want to ask. So the first one is whether we are able to tell at all, looking at the signature and at the types, whether this function can respond with any error status. So I would say no, because the only way for this function to fail is by throwing an exception. And this is not denoted in the signature. From the signature, you know that in the happy path, it's going to return a user, but that's it. If an error happens, so if an exception is thrown, do you know what happens to that error? I mean, if you don't have an explicit try-catch here, like if you are lucky, there is an error handler somewhere in the hierarchy. But if there isn't, your user may end up with just getting a stack trace in their screen, and that's not good. And the next question that might seem unrelated is whether goto statements are good. So what does it have to do with goto statements? Actually, if you think about what goto statement actually is, and it is a way of jumping to a pretty random place in your code for changing the control flow of your program. And then if you think about exceptions, exceptions are pretty much the same. So if you throw an exception, you don't always know where in the control flow you are going to end up. Because if you had a try catch clause here, okay, you would catch the exception here, and if you have the proper filtering in the catch clause, you would catch your exception there. But if not, it's going to end up in a kind of random place somewhere else if you have a global error handler. So this is, in these terms, the exceptions are quite similar to goto statements, and because of the fact that they introduce some randomness to the control flow, this is really not a good thing. So let's think what would happen if instead of using two different mechanisms to return a value and to signal an error, what would happen if you used a single mechanism for that? So what would happen if errors were also values? This actually has the benefit of having a unified approach because everything is a value. So no matter whether the value represents a success or whether it represents a failure, it's still a value. Of course, you should have like a global error handler for some truly exceptional cases that are totally independent of you. But for cases where you have things like business or domain errors or whatever you call it, it's really a good idea to represent them as values, similarly as we do with the successful values. So let's see if we can adjust our code to do it like that. So what we would need to start with is some type that would represent the value for us. That will also be capable of representing errors. So not only successful values, but errors. So let's start with an interface called attempt that would have a generic parameter. And this interface would have two implementations. So the first one would be called a success with the generic type, and it's going to have to hold the value of that type, and it implements attempt of A. And then we will have a similar case for failure. This needs to have the generic parameter as well, but since this is going to represent an error, it's actually not going to wrap a value of type A, but it's going to wrap an exception. So anything of type exception, it's also going to implement the attempt of A. And now with this tool, let's see how we can use it in our code. So let's get back to our service where we had this very simple way of looking up the user by ID. And let's see if we can do better. So now we want to change the signature of our method to return, instead of returning a user, it's going to return an attempt of users. So which can, already by looking at the signature, you can see that the function may fail. So it would return either a successful value, that would be a user, or a failed value, which would be an exception, but wrapped in a data class. And here, well, there is no magic here. What you need to do is to use the try-catch clause. So you need to basically try to run the existing method that we have and wrap it in a success. So if we write new attempt success, and here we just call the existing method, define user by ID, that would be our successful case. And if this fails, so if we have an exception, we need to wrap it in the failed variant of our attempt. So here we say return new attempt failure of the exception. So this kind of wraps our existing logic, the one that had like inconsistent ways of handling failures and successes, into a way that has this unified. So it has it gives us a type that represents both the successful and the failed variants. And now, if you get back to our API, and let's see what we can do. Like, how is this better? Because for now, okay, we have the wrapper, but what does it give us? So here, what you could do, you have the user that is returned by the service call, and its type is an attempt of user. So now you somehow need to check like what variant was returned, what variant of the attempt was returned, whether this was a success or failure. So, like in a naive approach, you could just use the instance of thing. So you can say if user instance of, and then you can say attempt success of user u, and then you can return the response with the user. So you can put a user here, for example. And this already, and if of course you need an else clause here for handling the failed variant. What you can see here already is a great addition to the recent versions of Java, which is pattern matching on records and even on nested structures. So this here in the instance of part, you can see that we actually decomposed the nested structures. So we had a user that was nested into the attempt in the attempt success, and using instance of, we are able to deconstruct this. This is type safe. So if you put a dot here, you can see that we have the methods from the user here. So the compiler knows that this is a user, and actually it would still know this even if we put a var here. So we don't need to actually be explicit about the type. We can let the compiler infer the type, and you can see that you can still have the ID and the name here. Okay, so that's good. So like you could do the instance of stuff, but this is not the best that you can do. So there is a better approach that lets you use a switch. So now, if you remember switch from earlier versions of Java, the switch was a pretty simple thing. You could match on constants and then return a value based on that. But in the recent versions of Java, switch was improved significantly, and it now lets you do pattern matching. So actually, what you can do here, you can switch over the user, and then you have in the case statements, you can do pattern matching similar to what we did in the instance of. So again, we can say at an attempt success. You already know that we can put a var here, and then without using the return statement, you just do response OK and u, and then you can have a similar case for failure. So if we put failure here, and we are going to have sorry, too much arrows. So it's like that. And we have some a response server error, I think, that we can pass the message to. And now another nice thing about switch is that it's no longer a statement in the recent versions of Java. It's an expression, which means that it has a value. So instead of doing a return in every match here, in every case clause, you can actually just put a return here. Because whatever you return here in the case clauses in the matches is going to be the value of the switch statement, which means that you can return it directly. So this looks nice, but you can see that it's not compiling for some reason. And if we look at the compiler error, it tells us that the switch statement doesn't cover all the possible values. In other words, it means that it complains that the match is not exhaustive, so that we didn't cover everything. And there is a nice way to solve it. If we get back to our attempt interface, you can see that, like, by looking at that code, you can tell that we covered everything, right? Because we covered success, we covered failure, and that's it. But the compiler doesn't know that. But we can help it know it by putting a sealed keyword here. And the sealed keyword here means that we tell the compiler that all the implementations of the attempt interface are here. And now if we get back to our API, you can see that the compiler error is gone. And so by putting the sealed keyword into, and by creating a sealed hierarchy of the variants of our attempt, we told the compiler, we allowed the compiler to know that here actually all the variants are covered. Okay, so what we did here was wrapping our function call in a data class that told us whether it was successful or not. But what we did here, and like a tiny drawback of this approach, is that we are still using exceptions to represent our errors. And the question is whether it's always necessary. I mean, exceptions have a cost to them. And the question is if you are able to just use plain values which don't belong to the exception hierarchy in Java to represent the errors. And it turns out that this is also perfectly doable. Let's try to do it. Let's try to see how this is going to work. So we had our attempt interface, which looked like that. And now what we are going to do is replace it with another data class that is called OR. And you can see that it has two generic types. It has the left value and the right value. And by convention, the right value, we would say that this represents the success because like right is on the right side, but it's also the right thing. And left is going to represent an error. The way it differs from the approach with attempt is that here the error type, or the type that is on the left, is not fixed to the exception hierarchy. So you can actually put anything here. So let's get back to our service and try to do it in yet another way. So here we created yet another version of our find user by ID. Here, for simplicity, we are just returning a left variant, so an error variant to represent an erroneous response. But that's enough. Here we are focusing on the type signatures and the things that we can see from the type signature itself. So here from the type signature, you can immediately see that the function can return like one of two values. It can be either some error type from our error hierarchy or the user. And if you look at our error hierarchy, this is, again, an interface with records that implement it. And you are able to put anything you have here, you want here, to represent the errors, and you are not bound to the exception hierarchy at all. So we changed our service. Let's now change our API to see how we can handle that. So going back to our API, this is the code that we already saw. So we are calling the even better find user by ID from our service. Now it doesn't return an attempt. It returns an OR, which can either hold my error or the user. And of course, you will probably already expect that we are going to do some pattern matching here. So let's do it. So the first match that we are going to do is the right variant. For right, we are going to take the user. And the user has a name. It has an ID. So it has an ID and a name. And let's say that in this case, the response that we want to return would be just the username. So we are only interested in the name. So this would look something like that. And it turns out that this variable is used. So it's OK that we have it. But this variable, this match is actually not used. And so what if we could ignore it? And actually, in Java 22, there was the recent addition of the underscore, which represents something called an anonymous value. So this means that we still match on the structure on the user, because this is still structural pattern matching. So we have a right that holds the user with the fields, so the structure is there. But by using the underscore, we can say that we are actually ignoring one of the fields. So we just don't care. We only want the name. So now you can just put an underscore here instead of calling your field unused or anything like that. You are not using that. There's an underscore for ignoring. And again, we need to cover all the other cases here. So we need to have a pattern matching for left. That's going to contain the domain error that we implemented there, and it has a message here. And we are going to convert it to a server error with the message. OK, and we again see the compilation error. We already know what to do about this because we forgot to put the sealed keyword in our interface in the OR. So let's go back to. OK, actually we have it. So it should look like that, and then it will complain that you don't have it here. If you put the sealed keyword back here, it would tell you that you still didn't cover all the cases. So what happens? Like we have sealed here, but there's still the compiler error, but it should work. Like based on our experience with the attempt thing, it should be working. But it's not. If you look here, you can see that there is. Sorry, this is not the right class. It should be my error. Sorry for that. So we put sealed here. And now we can see that like it should fix our compilation, but this doesn't compile. So we have a compilation error here. Now what is the reason? The reason is if you look at the implementations of error, it turns out that not all the implementations are here. So we have domain error that is implemented here in this file, but we have also external error that is defined somewhere else. So outside of the compilation unit that the domain error is defined in. So outside of this file. Fortunately, there is a way to fix it, and the way to fix it is by using another keyword named permits, and we can let IntelliJ do this. So it turns out that if not all the implementations of your sealed hierarchy are in the same compilation unit, they can be defined outside, but then you need to explicitly list them using the permits keyword. So here we needed to add both the domain error that we have defined here, and we also needed to add the external error that is defined well externally to our permits list. And then if we go back to our API, well, it still says that that the match is not exhaustive because we didn't cover the external error. So now we know that our error case can have one more value. So we need to match on the left with the external error with some message. And then again, we can return the response with the server error with the message. Now the match is exhaustive, so we have covered all the cases. The compiler knows this because we have used the sealed keyword. We have used the permits clause that lists all the possible variants, even if they were defined outside of that compilation unit. So that's good. And there is one more thing we can do with the pattern matching. So we can have something which is called guard expressions. So you have a new when keyword that you can use here. And you can, for example, say that you only want to match on errors whose message starts with something. So, for example, let's say that our database errors are going to start with DB in the message. So we can add a clause like that, and this would narrow down the pattern matching to only those cases. For some reason, it again doesn't compile, so we can see why. And the thing is that we broke the order of things in the pattern match. Because if you remember how switch statement works, the same thing applies here. And the thing is that you need to go from the most specific cases to the most general ones. So here the case in line 55 is it covers everything that would also be covered by 56. So if we also want to match on the cases like on the messages, we need to move it to a line earlier because this case is more specific. So we need to have the specific cases first and the more general, like the almost catch-all, later. Sorry. And with this structure, with this order, this is going to work as we expected. So that's it for the error handling. And now since we saw how this looks in practice, I want to give you a bit of theory about that. And the theory that we used here is called algebraic data types. Algebraic data types are types, like types known from a programming language, that are formed by combining some other types. And we had two cases here that we saw. The first one was the record type, so the record keyword that we are using. And the record type in the world of algebras and algebraic data types is called the product or Cartesian product. This is because you can think of a class with the fields as something that represents a number of dimensions. The number of dimensions is the number of fields that the class has. And then if you have a value in each dimension, so every field has a value, this is like in a multi-dimensional Cartesian plane. So you have like a point in the multi-dimensional Cartesian space. And this is why it's called a product, or Cartesian product. The other thing that we saw, and this was the sealed hierarchy, so a sealed interface with implementations. This is called, like in the simplest terms, it's called a sum, or you can also call it a disjoint union or a coproduct. And this represents a situation where you choose between multiple things, but you can only choose one thing. So if you look at records or Cartesian products versus sums or coproducts, you can think of looking at aggregation versus choice. So in products, so in record types, you aggregate things, and in sealed hierarchies, so an interface with implementations, you choose one of the possible variants. The nice thing about this, and by using this approach to model your domain, like we did with the errors, for example, that you have a compile time guarantee that invalid states cannot be represented. Because if you have an error hierarchy that we used, for example, like you cannot represent a state that an error that cannot happen. Well, it could be an exception, but from your error domain, so from the definition, you can already see what states are possible, and you are at compile time, you are not able to represent a state that it's not possible, something that is not going to happen. So this is actually very useful, and it's a really great tool. So this was about error handling, and the theory for error handling was algebraic data types, where we have two kinds of them, products and coproducts or unions, and they allow you to represent like almost everything, as you could see. Another use case that I want to focus on is validation. So let's say we have a person record like that has a name and age, and we have some validation logic for the name and the age. It doesn't really matter. Let's say it represents a form that the user is submitting, and we want to see a couple of ways, two ways actually, to approach validating the fields. So the simplest approach, the first that you might think of, is using a type that you already know, which we called OR. Actually, this name was like I chose it specifically, not to introduce the more typical name for that, which is either. We are going to use for the first approach the either type, which comes from an external library. It comes from Waiver. So Waiver is a library that allows you that introduces some functional concepts in Java. The bad thing about Waiver is that the maintainer has got back to real life and abandoned it for now. So it's kind of dead, and they are looking for people to maintain it. So if you have too much time, or if your company wants to support it, it's a really good thing to take over and to become a maintainer. So think about this. Okay, so coming back to our validation. In our first approach, we are going to use the either type to validate the name and the age. And you can see that the either type it's like exactly the same what we use in our OR approach, so it can have two values. The logic is pretty straightforward, so we have some common logic for validating. If the name is valid, we are wrapping it in a right. If it's invalid, we are wrapping it into a left. We'll do the same thing for age. So we'll validate it with either. There's no new stuff here. And now the last thing that we need to do in our validator is to somehow combine this into an instance of the person. When both of the fields are valid, we want to return a valid person. So this is like a pseudocode logic of what we want to do. So if the name is valid and if the age is valid, we want to wrap it in a value that represents a person. Okay, so let's start with validating the name. And then we need to do something with that. The thing that we want to do is, once we validate the name, and if the name is valid, we also want to validate the age. And then if the age is also valid, we want to wrap it in a new instance of a person. So here, what we need to use is a combinator method called flatMap. So you are probably familiar with the map method on collections. So it lets you apply a function to all values in the collection. FlatMap, in this case, so if you had a map on an either, it's pretty the same. So you have a value that's wrapped in an either. If you map over it, you can apply a function to that. FlatMap is pretty similar, but FlatMap expects that the function that you are applying returns the wrapper. So it doesn't return a value, but it also returns an either. So in our case, after we validate the name, we want to call validate age, which also returns an either. And this is why we need to use flatmap, because we want to have a function that also returns an either, and then we want like flatten it. So we would have an either of an either, but by flattening it, we are collapsing it into a single either. So we have a name here, let's call it n, and then if this was valid, we are calling validate age. And now, after the age is valid, we want to apply another function that would be the constructor of the person, because once we have the age and the name that are valid, we are already able to use them and to pass them to the constructor of the person. Since the constructor of the person class returns a value that is not wrapped in anything, it's not wrapped in an either, we are okay to use a map here. So previously we needed to use flat map because our function returned a wrapper, the either. Here our function, which would be the constructor of person, just returns a value, so it's okay to use map here. So we can call the valid age a here. And here we can say that we just return a new person of name and age. Of course, we want to return the entire thing. We need to adjust the return type. So now it should look okay. And again, if you look at what happened here, so we took the name, validated it. If it was valid, we called another validation, which is validate age. And then when both of the values were valid, we returned a new instance of the person. The important thing to notice here is that the error part of the either, so the left-hand side, is a single string. And this means that if there were multiple errors during the validation, so if you think what would happen if both the name and the age were invalid, you would only get the first error message. So if the name validation failed here, you won't know anything about the age. And if you look at it from a perspective of a, for example, web form that is submitted, so normally if you submit a form that has multiple fields, you would expect that like if you put an invalid value in the first field and in the third field, you would get all error messages immediately. It's not great user experience if you only get the error message for the first field, and then when you resubmit it, only then you learn that other fields were invalid as well. So this approach, which is kind of like fail fast, is not really good for a use case of validating a form, for example. And this can be seen from the signature here. So you are only getting, even if there were multiple errors, you wouldn't learn about them. You would only get the first error. So this behavior is called failing fast or short-circuiting. So it is going to fail whenever on the first failure. So since it's not perfect, let's look at an alternative. So whether we can do it better, still in the context of validating a form. So it turns out that there is another type in waiver that's called validation. And if you look at the signature, it's kind of similar to either. So it always also has two values, like the valid value and the invalid value. So we'll see shortly how this is different. So we are validating the name here. We are also validating the age using the validation type. So this is similar to what we did with either. And now we need to combine those. And again, the pseudocode for combining that is that we have valid name, valid age, and we want an instance of the person. So if we call validate name on the name, you can see that like we get the different types. So we don't get an either anymore. We get a validation. And the validation doesn't actually have a map or, well, it has a flat map, but it's not what we want to use. It has another interesting method that's called combine. And it lets us combine this validation with another validation. So let's use it, and let's combine the validation of the name with the validation of the age. And now we can call this combined. And you can see that like this is an instance of like this is some builder that has some generic types. It doesn't tell us a lot so far. Now, what we want to do, like if you look at the type here, it's not a coincidence that we have a string and an integer here, because the string and the integer, they represent the name and the age of the user. So we can say that we have those two values, the name and the age, wrapped into some kind of our wrapper, which is the validation right now. And now what we want to do now is we want to apply a function. So the function, again, would be the constructor of the person record. So having those two values wrapped in some context, the context is validated right now, we want to apply a function and then return a value in the same context. So after applying the constructor of the person, we still want to get the person in the validated context. And to do that, there is a function called AP. Why is this called AP? I will explain shortly. Let's just use it for now. And you can see that it expects a function that takes two parameters, a string and an integer, and this is the function that is going to build our person. And in our case, it's going to just be the constructor of the person. So we can just pass person.new here. We want to return the value. We want to adjust the return type. And now if you look at the signature here, this is the important part. You can see that it's different from the either case. So in the either case, we had a single string here. Here, we have a sequence of strings, which means that when we perform our validation, it's not going to fail fast. So even if the name validation fails, it's going to proceed, it's going to validate the age, and what we are going to get here is a sequence of error messages. So that's great, because this would give us all the error messages that we could present. Of course, the types are a bit different here, because the sequence here, this is from waiver, but this can be converted to a Java list. And if your API expects eithers, you can also convert it to an either, which will still preserve all the error messages. So on the left-hand side of that either, you would have the sequence or the list of strings. So that's I'd say better approach if we wanted to use this for a case of validating the form. And this doesn't fail fast. It combines or accumulates the errors and gives you all of them. So similarly to error handling, we had some practice. So let's now go back to a theory for that. So the either thing, and this is where the magical M word occurs for the first time. This is a monad. And monad is a construct that allows you to sequence computation or to do something that is called a monadic composition. And the property of monadic composition is that you can sequence operations that depend on each other. So the next operation requires the output of the previous one. And the important property is that it's failing fast or short-circuiting. So the either class that we used here is a monad. And this was the first approach. The other approach that we are using with the validation is called an applicative functor. And this is why the method was called AP, because this is from apply from the applicative functor. And the property of an applicative functor compared to the monad is that it's not short-circuiting, it's actually accumulating the results. So you can run the computations independently. They don't need to depend on each other. In our case, they did, but they don't need to. And then you are accumulating the results. And as a result, as we saw in the validation example, what we got was a validation with all the error messages on the error side, so on the left side. So this is like the theory for that. Okay, so that's it for error handling and validation. I don't think I have time for the bonus. So if you'd like to hear the bonus, you can come later. I don't want to take the break away. So let's jump straight to the takeaways. Okay, so the first takeaway would be that I would encourage you to try to start thinking in terms of pure functions and immutable values. As I said, it might be counterintuitive because if this doesn't make sense for you, that's perfectly fine. It didn't make sense for me either for quite some time. But this is useful. We saw the properties and the benefits that pure functions and immutable values give us. The second thing is that try to think about everything that happens in your program as a value, so even for the errors. So try to unify the way you represent your domain. If you have errors, you can represent them as values. You don't need to have a separate mechanism for returning successful values, which is just a value, and for errors, which is exception, throwing and handling exceptions. So, and this could give you some unification. This can give you better control with pattern matching, for example, over the states that can be represented in your code. And you learn about this at compile time, which is also great. I hope that you were able to see that the pattern matching is pretty powerful. So I really encourage you to explore. I wrote a blog post about the new switch expression and all the pattern matching stuff, so feel free to have a look at this. I hope that I was able to show that the category theory constructs like monads, applicatives, applicative functors, if you understand what they do, actually, you still have the theory behind that, which is like a lot of maths. But I think it's very important for a start to grab the idea. And then once you grab the idea and you start looking at the code, it's like easier to comprehend. So again, monads are things that let you sequence computations, and then the sequencing fails fast if something happens. And applicative functors let you combine everything and give you and accumulate the results. This was about the bonus, so I would only leave the link to the blog post with a mysterious name, the case against annotations, which is an interesting read by Adam Warski. This is from a couple of years ago, but I think it's still very relevant, so feel free to have a look. And if you like to learn more, please come here during the break. And if you wanted to read a single book about functional programming to grab the concepts, the basics, I really recommend Functional Programming Simplified by Alvin Alexander. This is based on Scala, but there is the book mostly focuses on the concepts, and they are introduced in a very straightforward way. You don't if you are able to read Scala, even if you are not, they're introducing Scala along the way. And Scala is a nice language anyway, so it's a good opportunity to learn it. And that's all I had. So thanks a lot for your attention. I think we have, this was meant to be faster. Thanks a lot, and I just switch to Slido for a second. Okay, Scala had these features for more than a decade, but was largely hailed as too complex. Why is the same in Java considered acceptable? Well, whether it's acceptable or not, I think it's a matter of preference. And I think the ideas are, well, they might be complex, and whether they are too complex or not, it's not. I'm not here to judge this, but I think it's at least worth trying and worth trying to understand them, based on some simple examples. So actually, Java is heavily inspired by Scala in terms of these features. And I think that in the case of pattern matching and the structures, I'm not sure whether it's too complex. I mean, it's a different thing, and change is always hard. So switching to this way of thinking might be hard, but I think at least that is worth giving a try. Will this code be available? Yes, it would. There is a GitHub repository. It's not updated, I updated this talk a bit, so I'm going to push the changes probably today or tomorrow. So this is the repository. I'm going to tweet this perhaps, so after I update it, so look at Twitter for the GeeCON hashtag, and it would be there. The nice coloring schema, okay. So this is done by, IntelliJ has a feature for highlighting to-dos. So if you go to to-dos, you can have custom highlighting for to-dos. And what I did, I also created, this doesn't need to be a to-do, this can be anything. So I have patterns for questions, for example, for regions, and I'm just applying, and here you can apply various schemas, so for color schemas. So look for the to-do settings in IntelliJ, and then you can use any pattern and provide arbitrary colors for that. These features or techniques come from Scala. Let's see, if you want FP, shouldn't we use a language designed for it? Well, of course, you could use a language designed for it. And as I said, when I spoke about having manageable side effects, well, Java doesn't give this. We already introduced the monad keyword, so the thing to manage side effects is called an IO monad, and this is a thing that you have in Haskell, in Scala, in some of the libraries that lets you manage your side effects so that your code is still pure and you have side effects. This is not yet there in Java, and I think due to some limitations, it's never going to be there. So if you need things like that, like managing side effects, you would need to switch to another language. But at least if you are still forced to use Java, you can at least use some of the techniques. And I think they can already improve your code base and improve the maintainability, the readability. So you cannot get everything. If you need everything and you are allowed to switch to a different language, well, you can try Scala. But if you need to stick to Java, there is still hope, and there is still some nice stuff you can do. Okay, I think this was the last question, so thanks again a lot, and I'm going to tweet this with all the resources. Thank you.